What's inside a black hole? Black holes are mysterious and bizarre objects in the universe that really have no explanation. In fact, we hardly know anything about what lies inside a black hole. We know and understand what we see on the outside of a black hole, but we have no way of going inside one to take a look at what is really happening. Even if we sent a probe inside a black hole, it would not survive the journey, and there would be no way that the probe could transmit a signal outside once it had been sucked inside. This is because a black hole is the product of mass being squeezed together so densely and tightly that it creates a gravitational pull so strong that not even light can escape its grasp. Supermassive black holes, with masses millions to billions of times that of the Sun, are thought to lurk at the hearts of all galaxies in the universe. You may notice that when you see a photo of a spiral galaxy such as the Milky Way, the center of the galaxy is a giant mass of light. Many people might think this looks like a massive sun, but this is not light coming from the black hole itself. Remember that light cannot escape the heavy gravitational pull. Instead, the light we see comes from magnetic fields near a spinning black hole that propel electrons outward in a jet along the rotation axis. These electrons produce bright radio waves. Quasars are believed to produce their energy from massive black holes in the centers of galaxies where they reside. Quasars are so bright that they drown out the light from all the other stars in the same galaxy. You might wonder, what's a quasar? A quasar is short for quasi-stellar object, and is a highly energetic phenomenon surrounding an actively feeding supermassive black hole. In simple terms, the supermassive black hole in the middle of a galaxy feeds intermittently. As it feeds, gas swirls around it at incredible speeds, forming an insanely bright, hot orbiting disk. If the black hole consumes a large amount of material, this feeding process is accompanied by gigantic jets of gas called quasars. These jets are fueled by the black hole they orbit. Some supermassive black hole giants release extraordinary amounts of light when they rip apart stars and devour matter, likely driving the energy of these quasars. When material gets too close to a black hole, it forms a bright, hot accretion disk around it. This accretion disk heats up to millions of degrees, blasting out enormous radiation. The magnetic environment around the black hole forms twin jets of material that flow into space for millions of light years. This phenomenon is known as an active galactic nucleus, AGN. The diet of known black holes mostly consists of gas and dust that fill the otherwise empty space throughout the universe. Black holes can also consume material torn from nearby stars. In fact, the most massive black holes can swallow entire stars. Black holes can also grow by colliding and merging with other black holes. This growth process often reveals the presence of a black hole. Supermassive black holes, however, are not always feeding. If a black hole runs out of material to consume, its jets lose power and shut down, until something comes too close and the system restarts. The supermassive black hole at the center of the Milky Way is currently dormant, as it has no material to consume. It lies as a sleeping giant without an active galactic nucleus or quasar. However, when the Milky Way collides with the Andromeda Galaxy in approximately 10 billion years, our supermassive black hole may awaken as a quasar when it begins consuming parts of the new galaxy. Despite their reputation, black holes are not as dangerous as they might seem. While it is true that any object carefully dropped into a black hole would be lost forever, black holes are not particularly efficient at pulling material into them. There are two reasons for this. First, black holes attract objects only through gravity, much like how the Sun keeps the planets in stable orbits. Most of a galaxy's stars and material remain in stable orbits around the central black hole, with no reason to fall into it. Second, black holes are inefficient at drawing material close enough to cross their event horizon and be consumed. Even small black holes are better at tearing apart companion stars than growing their own mass. For example, if the Sun were replaced by a black hole of the same mass, Earth and the other planets would continue orbiting as they do now. Darkness would fall, but Earth would be at risk only if it came within about 10 miles of the black hole, far less than the actual distance of 93 million miles that separates us from the Sun. So, what lies inside a black hole? Current theories predict that all the matter in a black hole is compressed into a single point at its center, known as a singularity. However, we do not fully understand how this singularity works. Properly understanding it requires a fusion of the theory of gravity and quantum mechanics, a yet-to-be-realized unifying theory known as quantum gravity. This remains one of the most significant unsolved problems in physics. Einstein's theory of general relativity allows for unusual possibilities in black holes, such as the idea that a singularity might form a bridge to another universe, similar to a wormhole. Wormholes, solutions to Einstein's equations, might allow for travel to other universes or even time travel. However, without observational or experimental evidence, these ideas remain speculative. In contrast, the existence of black holes is well documented, and we understand how they form. What lies inside them, however, is still a mystery. Do black holes live forever? Surprisingly, if a black hole has no material to consume, it does not. Stephen Hawking, a renowned physicist, predicted that black holes emit radiation, now known as Hawking radiation. This phenomenon causes black holes to lose mass and energy over time, eventually leading them to evaporate completely. Hawking radiation is like a black hole recycling the energy and matter it consumed back into space as radiation. This process is incredibly slow for large black holes, but if smaller black holes existed in the early universe, they might have evaporated quickly in brilliant flashes. Though Hawking's insights are groundbreaking, the glow from this radiation is irrelevant for most known black holes, as it is negligible. In conclusion, black holes remain among the most mysterious objects in the universe. One day we might uncover their secrets, perhaps discovering that they serve as gateways to other dimensions or simply accepting them as they are. Whatever the case, the study of black holes continues to push the boundaries of our understanding of physics.